All right, today we're going to continue with our dive into related rates. And again, just a disclaimer, this is a very difficult section. I don't expect you to get all of these questions completely right the whole way. On all of these, on the AP test, these would be the free response questions where they're generally 4 or 5 parts. Each part you get 2 to 3 points for getting that specific section right. And these are especially challenging to teach virtually because I can't watch you do the steps and then tell you where you went wrong. So it is important that you show your work on this, and I can kind of identify maybe where you went wrong. It is also challenging because there isn't a specific formula that you always do this step and then this step and then this step. These are more critical thinking problems, which again are difficult to teach in our current environment. So just going to do the best we can on this, and we won't be able to spend as much time as I would like to on these either, nor can I watch you do them. So some added challenges, but we just got to do our best to persevere in these unfortunate circumstances. So with that being said, let's go ahead and get to it. As I said in the last video, this is kind of just a general strategy layout. We always want to draw a picture. We always want to identify whatever formula we're going to use. We want to identify what we're given, use appropriate variable labels, identify what we don't know, what we need to find, use appropriate labels with that as well. You also might choose different labels than I would choose as well, and that's perfectly fine as long as you're consistent with your labels. We are then going to implicitly differentiate. After we do that, we're going to plug in our given variables after we differentiate, and then solve for the unknown variables. Now there is one situation, and I'll show you where we can actually plug something in before we differentiate. So I'm just going to make a little note here. And it might not make sense until we do a problem that illustrates this, but we're going to say if the variable doesn't change, then we can sub before differentiating. You don't necessarily have to write that yet, but I'll show you what I mean by this. It makes things a little bit easier. So if the variable doesn't change, then we can plug it in before we do our implicit differentiation. So that being said, let's go ahead and get to it. Our first example, since we're getting close to the new year, here's an example about the New York ball drop on New Year's Eve. So let's draw a scenario for this. So we've got the New York ball drop, and you're looking at it from a distance of 100 meters away from the base of the structure. So you're standing out here, and you're approximately 100 meters away from the ball. The ball is going to drop at midnight at a constant rate, so it's going to fall this way down that tower. We're asked, and that constant rate is going to be 2 meters per second. The question is, what is the rate of change of the angle? All right, so this is a new scenario. We've got a rate of change of an angle. So there's an angle that's formed by you up to that ball. We're going to always call that angle theta. Just as generally used for every single problem of this type, theta is just kind of the x of Greek letters, I guess you could say. So theta is going to be our angle. The question is, if it drops at the constant rate, what is the rate of change of the angle between you and the ball when the angle is pi over 4? And it doesn't explicitly say this, but this should say radians as well. So as a note, make sure your calculator is in radians. If you want to double check, just hit mode, go down, and then make sure it says radians and not degrees. So that is in radians. All right, so where do we begin? Well, think about what's happening here. This ball's going to drop. So as that drops, this angle theta is going to change because as it moves down, the angle is going to get smaller and smaller, right? Also, let's go ahead and throw in some other labels. Let's just call this side of our triangle x. Let's call this side y. We could call this other one up here z if we want to as well. It doesn't really matter. And let's notice a few things. First of all, we know x. X is 100. We also know that x doesn't change because even as that ball falls, you're still going to be 100 meters horizontally from that ball. So dx dt is 0. Y, we don't know. And we do know dy dt though, because the rate that it's dropping, it says negative, well, it says 2 meters per second, but since it's getting smaller, we're going to say negative 2 meters per second because it's falling. That means y is shrinking. Z we're actually not going to worry about, and you'll see why in a sec here. The reason why is because we're going to use a trig formula, a trig ratio, in order to solve this. And Z is kind of irrelevant. We're not going to be doing the Pythagorean theorem in this because it asks us a question about an angle. It doesn't ask us a question about the distance between the person and the ball or something like that. If it asks us like, you know, what's the rate of change of the distance between the person and the ball as the ball falls, then we'd be concerned about Z, but it's not. It's asking us about the angle. So we're given no information about Z. We're not going to worry about that. So we do know theta is pi over 4. And we're asked, what is the rate of change of the angle? So whenever you see rate of change, think derivative. In other words, d over dt in this case. So we're going to call this variable d theta dt. That's what we want to figure out. How do we figure that out? In any scenario where you're asked to use an angle, think a trig ratio. That is going to be our magic formula, a trig ratio. So our first task is to figure out what trig ratio we want to use. There's only going to be one good choice. So we've got an angle, and then the two variables we're talking about are x and y because it gives us some information about x and it gives us a dy dt. So we want to use those two sides. If we're looking, we've got an opposite, right? And we've got an adjacent right here. So think about what trig ratio SOHCAHTOA has an opposite and an adjacent. Well, that's going to be tangent. So the ratio we actually want to use is tangent of theta, and then let's go ahead and write her out, equals opposite. Opposite is y over adjacent, which is x. All right, so that's good. This is our formula we need to use. This is our related rates formula because it related the rate of our theta, which we'll see when we differentiate, to the rate that we're given, which is dy dt. It's going to allow us to relate those two. All right, so at this point, typically what we'd want to do is differentiate, right? So we would take the derivative of tangent, which is secant squared, theta. Now, since we took the derivative, we also have to throw on a d theta dt. Sorry, that keeps changing, guys. So d theta dt. With this other part, since it's a fraction, we would actually need to use the quotient rule. Don't forget, you can't just take the derivative of each one. You got to use the quotient rule. So we take the derivative of the top, which should be dy dt, times the bottom, minus the top times the derivative of the bottom, dx dt, over the bottom squared. So we got some extra stuff going on here. We could go ahead and plug in. But if you remember, I'll just pause here a second. I told you that if the variable doesn't change, then we can actually substitute in before we take the implicit derivative. I mentioned at the beginning, x doesn't change, right? Dx dt is 0. So since x doesn't change, we actually don't even need to do the derivative with it in there. We could actually not do this. It's okay if you did this. It would still work out just fine. But since x doesn't change, I can actually just go ahead and replace x. I can just write this as tangent of theta equals y over 100. And then I could take the derivative. It would be secant squared of theta d theta dt. And that y over 100, that's kind of just like 1 over 100 y. So it's just like a constant. So it would just be like 1/100th dy dt. which is a much simpler formula than the one above it. So if you can replace, in other words, if it doesn't change, then we're allowed to replace it. It would end up giving you the exact same answer, I promise, but this just makes it far easier. So let's go ahead and plug in then what we know and we don't know. So secant squared, theta, we know theta, it's pi over 4. We don't know d theta dt, so we gotta leave it there. It's okay because we're trying to figure out. Equals 1/100th dy dt, and we know dy dt is -2. All right, now notice if we had done this one here, we would need a y as well, which we don't know what y is. We'd actually have to use the tangent formula to figure out y, so it would be an extra challenge at that point. So this is definitely a far easier way to go. All right, so let's just simplify this a bit. Also a reminder to never round until the very end. So this -2 times 100 is just be -2 over 100. Secant squared of pi over 4 times d theta dt. So we want to just go ahead and divide the -2 over 100. It actually is an easy decimal, just 0.02. So this is just -0.02. So what we end up with is d theta dt equals -0.02 divided by secant squared of pi over 4. And that would be our answer to get d theta dt by itself. Right. That looks a little easier than it actually is. If you go to type this in your calculator, you're going to run into a problem because you're not going to see secant on your calculator. So another thing we have to be comfortable with is our trig ratios and knowing what's another way to write secant. And remember, secant equals 1 over cosine. So how we actually need to type this in is -0.02 divided by, another thing to remember is this secant squared is the same thing as secant of pi over 4 quantity squared. It's like writing it out there. So this is going to be 1 over the cosine of pi over 4 quantity squared. That's how we have to type that in, because the secant of pi over 4 is the same thing as 1 over the cosine of pi over 4, and that whole quantity has to be squared. So we want to type it in like that, -0.02 divided by parenthesis 1 divided by cosine of pi over 4. Again, make sure your calculator's in radians, and you want to square that whole denominator, and you will get -0.01. And the last thing we need to think about is what is the units here. Well, our angle is in radians, and it is a rate of change because it's a d theta dt. So it's going to be a radians per second. Radians per second. That is our answer. Whenever you're trying to find a rate of change, make sure you've always got like a fraction as your unit. This, in this case, is a radian per second. We've got a unit per time. So that is our final answer. All right. Let's go ahead and look at our second example. In this one, we have a cylindrical fountain that is filled with juice. This really should say can. Now the can has a 10 centimeter radius. How fast does the height of the juice in the can drop when the drink is being drained at 5 centimeters cubed per second? All right, so first thing we need to do is draw a cylinder. Hopefully you remember what that looks like. A cylinder has a circle on the top and the bottom. Generally on these questions on the AP test, they do actually give you like a little picture. So don't worry about if you're bad drawing or bad visualizing these. Normally they do give you the picture. And also they do give you the formula that you're going to need for this one. But let's see if we can come up with that formula first of all. All right, so this thing is filled up with juice, and then the juice starts to be drained out of it. So sort of what's happening here is the juice inside of this starts to drop. Juice level drops, right? And what the question is, how fast does the height of the juice in the can drop when the drink is being drained at 5 centimeters per second? Centimeters cubed per second, sorry. Centimeters cubed. When you see this cubed, you should immediately think volume. If you think squared, squared equals area, cubed equals volume. So that unit right off the bat, centimeters cubed, is telling you that we're going to need a volume formula. You probably don't remember what the volume formula is of a cylinder. That will be given to you. That is pi r squared times the height. It's basically the area of the base times the height. And the area of the base is a circle. Area of a circle is pi r squared. So we multiply that by the height. All right, so good. We got some good variables in there. It tells us about the volume. We're going to be asked something about the height. And then it also gives us some information about the radius. So that's great. So we have a 10 centimeter radius. So radius is 10 cm. Let's think about if the radius, if it changes. Well, this is a cylinder. The radius, no matter where you move, the radius is always still going to be, no matter what the level of that juice is as it moves down, is always going to be 10 centimeters. So the good news is dr dt is actually going to be 0. Now, if this were a cone, the radius does change in a cone. So you'll actually see that in the next problem. We couldn't replace it, but in this one, we're going to be able to replace 10 at the outset because it does not change. The other information we're given is height, right? We're going to be asked something about height. How fast does the height drop? So we actually want to find dh dt. How fast does that drop? But it doesn't actually tell us anything about the height. We don't know it. We'll see if we need it. All right. So before we take the derivative, we can actually plug in some stuff. Well, at least one thing, and that is r, because r does not change. So v equals pi, r is 10 squared h, and let's just simplify this a bit. It becomes 100 pi h. All right, so that's good. That's not going to be too hard to differentiate because remember 100 pi is just a constant. So the derivative implicitly of this, derivative of v is dv dt, and the derivative of 100 pi h is actually just going to be 100 pi dh dt. So very good. That one's not too bad at all. Now let's take a look at the scenario the wrong way. If you had not replaced that at the outset and you took the derivative, it'd be dv dt equals, you'd have to do a product rule. So you would do 2 pi r dr dt plus pi r squared. Oh, sorry. This has an h on it as well. Plus pi r squared dh dt. So then you would have to plug everything in. When you did so, dr dt would be 0. So this whole thing would go to 0. So it would end up going away. And you would still end up with the same pi r squared dh dt, which would then be just your plug in your 10. So you'd end up at the same spot. It's just you got some extra work here with doing the product rule that you don't really need to do. So if you forgot to plug it in, it's not the end of the world because the 0 would just take everything away. You wouldn't actually even need to find h because it would just get multiplied by 0. But it just saves you some work if you can identify if a variable doesn't change, then you can plug it in. So, all right, so let's go ahead and finish solving this. We're trying to find dh dt. And it does tell us dv dt. I guess I didn't write that out. Should have dv dt, which is being drained. Since it's being drained, it would be a negative 5 centimeters cubed per second. So that's going to be negative 5 equals 100 pi dh dt. So pretty simple operation here. We're just going to divide both sides by 100 pi. So dh dt equals negative 5 over 100 pi. And they might even, on the AP test, they might even just write this as negative 1 over 20 pi. Seen it that way. If this is a non-calculator question, which this very well might be a non-calculator question, you would just see it written like this as the final answer. With the units, then it is a rate of change, right? dH dt. And the units we're talking about are centimeters and seconds. So centimeters per second. So if this was a non-calculator, because notice we haven't actually used a calculator yet. So that's very doable without a calculator. If it was a calculator, then it would probably want it the decimal. So then you would just go ahead and divide it 1 divided by 20 pi. And you should get negative 0.157 centimeters per second. But I would actually expect this to be a non-calculator question. And this could be a free response where so one part of it is identifying the correct formula or differentiating it correctly here, and then plugging things in correctly, and then solving for dV dt correctly, and then also getting the units. This could kind of be the different parts of your grading here. Next semester, when we come back from Christmas break, we'll try to look at some more of the AP questions and see how they grade it so you can get a good idea of that. All right, and let's do one more together. This one, we have water flowing into a tank that is in the form of an inverted cone. And we're going to draw this, but again, you would probably get a picture of this, so don't freak out if you're not sure how to draw this. An inverted cone, think of an ice cream cone. That would be a normal ice cream cone. If you invert it, it would be an upside down cone like this. So that's an inverted cone. This inverted cone has an altitude of 16 meters. Altitude is referring to sort of the height. Altitude, height. It's the vertical height from like the center of the cone to the top. It is not the slanted part. That would be called the slant height, referring to just the altitude. So altitude is 16 meters and a radius of 4 meters. So radius would be from the center out to here. So that's 4 and that's 16. And this is being flowed into at a rate of 2 meters cubed. Okay, cubed. Boom. That tells us volume, and it did give us a volume formula. So that's good. How fast is the radius changing at the instant the radius of the tank is 2.5 meters? So water's flowing into this, and as it flows into it, water's sort of going to start to flow up, right? It would start to fill up. So it's going to sort of be moving up that way. All right, let's see if we can figure this out. Let's start by identifying some stuff here. Notice it gives us 16 and 4 sort of as our baseline. But when we're actually going to measure it, the radius is going to be, when we want to know it, is going to be at 2.5 because we're going to be up here somewhere now. So it is going to be changing. So that 16 and the 4 are important, but they're not actually going to get plugged into our volume formula per se. So let's go ahead and take that formula. Also notice that we gave our volume is 2 meters cubed per minute, so that would be our dV dt, which is 2. And our radius, when we actually plug it in, is going to be 2.5. All right, now if we were to just go ahead and take this volume formula, pi over 3 r squared h, similar to a cylinder. The difference is it's just 1/3. It's like 1/3 pi r squared h. The 1/3 is the only thing that's different. And the reason why is a cone actually has 1/3 of the volume of a cylinder. It's kind of a fancy way of doing that. All right. When we're ready to do this now, you might want to go ahead and think about if anything doesn't change. It doesn't tell us anything about how fast the height is changing. It doesn't tell us that. DHT, we don't know that. We do want to figure out how fast the radius is changing. So we don't know that either. So if we were to just start from the outset and take the derivative, this isn't going to work, but I still want you to see why it won't work. I'm going to go ahead and take the derivative. I can't replace r or h. One, because I don't know h, and I can't replace r because r does change. So I can't replace anything in this. So if I were to differentiate this implicitly, it'd be dV dt. equals, we'd have to do a product rule here. So it would be 2 pi over 3r dr dt times h, and then plus pi over 3r squared dh dt. So this is kind of a mess. There's a lot going on here. And there's also a lot of things I don't know. The only thing I do know is r, but I don't know dr dt, and I don't know h, and I don't know dh dt. So we can't really solve this, because if I started plugging things in, I would get 2 equals 2 pi over 3. R I know is going to be 2.5. dr dt I don't know. H I don't know. And I could plug in R again, but I don't know dh dt. So no way at all we could solve this. There's way too much unknown stuff. So this is not going to work. But it did give us some other information, right? You're never going to be given information that you don't use. In this case, it gives us 16 and 4 as the dimensions of the original cone. So what we're actually going to do with that information is, notice in here I got a triangle that's formed, and then I got another triangle that's formed inside of it. So this is actually a case where we're going to use similar triangles. There are several related rates problems where you do something like this, similar triangles. It's a little bit more challenging, but I wanted to at least show you how to do something like this. So if you counter this on the AP test, you'll have at least seen it one time in your life. So what we do with these similar triangles is, with similar triangles, you learned back in geometry that the ratio of their sides are equal if they're similar. So in other words, if I call this big H 16, and if I call this 4 big R, right, and I were to write those as a ratio, 16 over 4, and then I called this 2.5 if I called that little r, and then I called this little h, the height of this smaller triangle. This would be equal to, so I did my height over my, my height over my radius equals my height over my radius. So this would be equal to h over 2.5. In other words, big H over big R equals little h over little r. And when I do that, you'll see I actually have a good little ratio here. So what I could do is just either solve for h and then plug that in, or the better thing I actually want to do is I'm going to find, erase this real quick, sorry. The proportion of R and H. R and H are proportional as it changes. I got to exit out of this, or else it won't let me write. Stick with me here. I'm going to write R and H as proportions. So I can actually substitute out H in this problem. Since I don't really know anything about H, I actually want to substitute it out. So I'm going to write this as little h over R. Then if I were to cross multiply, I would get 16R equals 4H. And I actually want to solve for H in terms of R so that I can just completely replace H in this formula, so I don't have to worry about it. So then H would be, having troubles here. H would be 4R. So just divide by 4 on both sides. So that up in this formula, what I could do is just go ahead and replace H, since I don't need H anyhow because we're talking about the radius, right? We're not talking about anything about the height. So I want to go ahead and replace H. Now be careful, you don't want to replace R. You don't want to solve it the opposite way and replace R, because we're trying to find how fast the radius is changing. If we replace R, then when we differentiate it, we're not going to get a dr dt. So what we're going to go do is just go ahead and replace H. We would now end up with V equals pi over 3 R squared, and H is equivalent to 4R. So in other words, the height of this thing is always 4 times the radius. And at the beginning, radius was 4, the height was 16, so that makes sense. So we could also figure out, if we wanted to, if the radius is 2.5, well, then the height would be 4 times that, so it would be, 10, right? But we want to just go ahead and replace it in terms of R, so we don't have to worry about a dh dt. All right, so we'll just simplify this a bit. We get 4 pi over 3 r cubed. And this is now where we want to differentiate. So then our derivative becomes dv dt equals, we multiply that 3 down. The 3's are going to cancel because 3 times 3, they would just wipe out. Give you 4 pi r squared dr dt. And this is good because I have no h's, no dh dt's. All I have is r's, dr dt's, and dv dt's. So let's go ahead and plug in here. dv dt was 2. It is filling up, so it should be a positive. Equals 4 pi. Our radius at this instant is 2.5 squared dr dt. So now we can go ahead and solve for dr dt because that's our only unknown. So dr dt, we're just going to divide 2 by all of that, 4 pi times 2.5 squared. And do that. And I believe you'll get 0.025. Let's double check that. Yep, 0.0254, which is around the 0.025. Always need a units. This is a rate of change. We're talking about meters and minutes. So the radius is changing at 0.025 meters per every minute. All right, I know that's a lot. I know you're probably confused in multiple ways, but just kind of use this as a baseline, this sort of steps here on this one. Same like on the previous one. Try to find a problem that you can use as a guideline and just follow the steps that I did. Also, feel free to Google similar problems. Try not to do the exact same one, but feel free to Google similar problems and just note the steps that they used in order to solve these. So, all right, guys, best of luck with that. Make sure you do reach out to me if you just want to connect on a Thursday or a Friday and want me to look at your work, or just come to my room and work on it some. Feel free to do so. I'd be more than happy to have you do that. All right, good luck.